Is my voice audible?
Yes, ma'am, audible.
Are the slides visible?
Yes, ma'am.
Okay, sure. Thank you. Good afternoon, participants. Today, we are going to discuss about the applications of AI and blockchain in power systems. So let's start. So these are the contents of our presentations: introduction, challenges, computational intelligence method, data analytics, model use for forecasting, comparative analysis of results, and references. So when we talk about applications of AI in power systems, it is highly and largely applicable to some of the major problems of power systems like forecasting of renewable generation, then electricity market prices, since our course is related to electricity, deregulated electricity system. So this is one of the major applications. And one of the other major applications in power systems is forecasting of load. And there are many other applications as well. So we'll be focusing on first two of this. So electricity price forecasting uses past market prices, demand, generator offers, fuel cost, and network constraints as inputs to machine learning and deep learning models to predict electricity prices, helping market participants optimize bidding and hedging strategies. So in the last one of my lectures, I discussed that electricity market prices, the spot electricity market price or day-ahead electricity market price, they create uh, huge they are a kind of huge volatile component for them to decide their strategic bidding, and as a result of which they require the forecasting of these stakeholders like generation company and distribution company. They require the electricity prices forecasting, and hence this has become a very important applications in electricity market operation. Then another is solar irradiance forecasting or renewable forecasting. It uses, so focusing on solar irradiance forecasting, it uses historical irradiance, temperature, and PV output to train AI models, which then predict solar irradiance to improve unit commitment and reserve scheduling. So wherever we have the input of solar power in power system operation problem or power system planning problem, in reserve scheduling problem, there solar irradiance forecasting is highly used. So this block diagrams gives a broader overview of how the solar irradiance forecasting can be done using AI model. So first we need the input, the data acquisition, which means we need the data to be input. So the data is real historical data of generation, demand, and electricity price. And then this is like a broader overview, and this is giving you about electricity price forecasting. So we do the data entry identification, then data cleaning, missing value treatment, outlier treatment, feature selection, data normalization. So after the data acquisition, the data pre-processing is done, and after then the splitting the data into training, then validation and testing. So here in this block, the training is done, validation is done, and the testing is done. So you forecast the load. This is the final, after data pre-processing, this is the data which is input. So load forecast, fossil oil gas generation, solar generation, onshore wind generation, electricity, forecast electricity price. Now this is input to training and testing of the proposed model. So this is giving an example of LSTM model, which is a deep learning model. So here we first validate the training model on first we tune the hyperparameters, then we input to sliding window stacked LSTM, and after that we do the training, and after that we validate the trained model on test data. And then the validation is done by, or evaluation results are done by calculating these error indices RMSE, MEE, R square, SMAPE, whichever is more suitable. So together these AI-based forecasts reduce uncertainty, support economic dispatch, and enable better integration of renewable energy into the grid. Now let's go to electricity price forecasting. So in earlier 1990s, process of deregulation and introduction of competitive markets have reshaped landscape of traditionally monopolistic and government-controlled power sectors. Electricity price forecasting has become an essential task for all the players of electricity markets. Just a second. 1 hour after 1 hour. More accurate the EPF, less will be the market risk. So, excuse me, just wait for a second. So here we have, if you look at this diagram, for whom the electricity price forecasting is essential task. So it is uh, the Genco. It is important for the Genco to optimize their procurement strategies according to electricity price forecast. And it is important for retailer companies to schedule their operations according to low price zones. And both of them work towards maximizing profit. So EPF is essential. Types of electricity price forecasting. So we have three types: short-term price forecasting, medium-term price forecasting, and long-term price forecasting. So now short-term price forecasting. So you have the time, the slot is few minutes to few days. Medium-term price forecasting, weeks and months, and long-term months to years. Short-term price forecasting is used to develop making strategies for intraday market. Medium-term price forecasting is used for future maintenance, scheduling of power plants, risk management, and plan future contracts in day-ahead market. Long-term is used for investment and planning, such as determining the future sites of fuel sources for power plants. So these are the influential features of electricity price forecasting. Uh, so renewable power energy, which is affected by wind, solar irradiance, and hydro plants, and then thermal plants, which is affected by gas price, coal price, CO2 price, oil price, and then storages, revisions, technical outages, and power grids. All these are the input parameters for electricity market, which affect the electricity price forecasting. These are the effects from the supply side. Then from the demand side, you may have cooling and you're affected by holidays, celebrations, and calendar effect, which affect the cooling and heating devices. Then another factor is cloud cover and lighting, and other is temperature, cooling, and heating devices. Then you have electricity price volatility. Then electricity price volatility is major challenge in price. So price volatility is major challenge in price forecasting. So EP is most volatile than any other commodity. So these factors affect the electricity price volatility, and other which can affect is, and all this is due to non-storability of power, generation uncertainty, outages, transmission congestion, and renewable energy sources integration. So now computational intelligence method. So disadvantages of statistical models, which were earlier used in place of AI, and what is the advantage of artificial intelligence over statistical models? So the statistical models were only accurate when data varies slowly. Electricity prices vary sharply, then statistical methods perform poorly. They have limited ability to capture the nonlinear variations of electricity prices and rapid variations in price signals. Computational intelligence method, they solve problems which traditional methods cannot handle efficiently, like have ability of to handle sharp variation of electricity price. And AI-based approaches have the ability to deal with the nonlinear relation between the price signal and its affecting factors. Hence, the forecast accuracy is increased. So, machine learning and deep learning models, um, this table gives an overview of different machine learning and deep learning models applied. So first is K nearest neighbor. It is a supervised machine learning algorithm, and it can be used to solve both classification and regression problems. It is very simple to understand and easy to implement and done, but it has poor runtime performance if training set is large. Next is supposed vector machine. It is a supervised learning technique, finding a hyperplane that best divides a dataset into two classes. Performance is more than other linear classifiers, but it requires high computational complexity and preserves the complex structure. Then you have another deep learning model, which is recurrent neural network, which is deep learning model. It is a time series model for electricity price estimation. It gives good prediction for time series sequential data of electricity price, but it suffers from vanishing gradient and exploding gradients. Then you have CNN, convolutional neural network. It is a deep learning model. It is used for EPF. It automatically detects the important features without any human supervision, but it is sensitive to overfitting and exploding gradient. LSTM, it is a supervised learning model of deep learning. It has the ability to work with sequential time series data, ability to handle long-term data dependency of EPF. It has the ability to handle problems of vanishing and exploding gradient. LSTM model is sensitive to different random weight initialization. LSTM model is sensitive to overfitting. So we will be discussing LSTM model here, and this will be taken up by my PhD student Ashish Prajesh. So over to Ashish.
Thank you, ma'am. So, okay, ma'am. Okay, thank you, ma'am. So over here, we will be looking for LSTM. Is my voice is audible to everyone? Kindly, can anyone please confirm?
Yes, sir, audible.
Oh, okay, thank you, Kush. So basically, over here we will be looking for LSTM. As the name suggests, it is long short-term memory. So basically, it have the upgraded version of RNN. RNN is recurrent neural network. So over here, yes. So basically over here, it is the updated version of RNN. So what is the problem that we have, ma'am have told earlier that the problem that RNN have basically like the problem of vanishing gradient, exploding gradient, the weight increases and decreases and the values of the forecast not become compatible enough. So that's why in order to overcome these challenges, we have moved towards LSTM, that is long short-term memory. Because of the unique probability, unique things in an architecture, it have enabled to remove the shortcomings as in RNN. So let's see in figure number 2, we can see the repeated model of LSTM. This is our repeated model, 3 model that we have seen over here. So can we have next slide now? Yes. So basically, if you can see the model, the one unit of an architecture can be seen over here. So as I've told you, it have a unit architecture. So in this architecture, we have 3 layers, basically 3 gates. So the forward gate, input gate, and output gate. So the main function of this gate is to remove this problem or that is there in existing RNN problem. So first of all, let's see what forward gate is. Over here, the LSTM identifies which informations are important, and it will throw back which informations are not important from the cell state. So this thing is done by the sig-model function. Over here, the input is given, and we are going to be giving it and passing it to the sig-model function. Once we got this information, what is more important, more relevant information, then we pass it to our input gate layer. So in input gate layer, it is a combination of two things, that is activation and 10H function. So over here, it decides which new information we are going to store in the cell state. So basically, as we can see, when the function is passed through the forget gate, then the output will be sent back to sigmodel and 10H function, and it will decide how which information is important. And afterwards, we have an output gate. Output gate is basically a sigmodel mathematical function and a multiplication of output with 10H function. So basically, this gives an output which is important and most relevant output that need to be put on the cell state. So basically, these are the 3 states which enables the LSTM model to overcome the existing problem of RNN. Yes, next slide. Yes. So basically, I have told you the basic how the LSTM look like and what is the inner architecture over it. So let's understand with the working of LSTM. Let's take an example. If we have 10 data points, we have from 100 to 101, 102 to 109. So how we do with LSTM? LSTM is like first of all we have to go with the data pre-processing. Data pre-processing, we will be dividing our sample data set into two parts. One is testing and one for training and one for testing. And for training, we will be utilizing 70% of data, and for testing, we will be utilizing 30% of data. So in training stuff, we will be like including the first 7 points as it is a 70% of the 10. So 101 to 106, and in testing will be taken 107 to 109. So after which the next key point in LSTM model is the time step that we are taking for. Like in time step over here, we are taking three. Three basically indicates like we will be taking three data points, three bunch of the points will be taking like 100, 101, 102, and we will be predicting the fourth point, that is 103. So of course the output that we have, it is a training process, it's a supervised learning process. We know our output over here is 103. So by forecasting the third point from 101, 102, 103, it might be 102.5, 3.5. There is some must be some errors. So that error we will be minimizing through the loss function MSC, that are objective function. We will and by the help we will minimizing it, and weights will be updated. So this is how we are working in the training process. So simultaneously, if that 103 will be given to the next portion, 101, 102, 103, and we'll be predicting the next fourth point. So this is how we are updating the weight and making the LSTM model compatible for data time series processing problem. And once our model is being trained, we will go for the testing point. In testing, basically, these are the unseen data which our model have not seen. So we will be evaluating our data, our results accordingly. So test points are those points not seen. So we will implement 107, 108, 109. So what will be the result? That will be the forecast value. So x-axis I am written over, but it might be 109.5, 109.6. So simultaneously we can see the output, the predictions that can come from here. This is how the basic working of LSTM, if you will see in the inner code. So let's understand how the inner process, like how the weights are updating. The things that I've told you, that it is feasible from the code point of view, but from the architecture point of view, let's see. So basically, it is feed forward backward propagation. And first of all, I will show you. So over here we are calculating what output will be. The desired output will be a combination of multiplication of weights and input xi. So input will be xi, and weight is the parameters which we are going to update in the training process. So over here we will be calculating the error. Error will be half of d minus d. So capital D indicates the actual output, and D is the forecasted one that we are coming across. So once we calculate it, then it will be a partial differentiation d by dw is equal to de by dd and de by dwi. So this is how, and we will get the error function over here is d minus d into xi. So our like we have come across this portion. This portion will be like our learning rate, that how it will be able to learn. So this point will be given to updation. So w new is equal to wi plus plus this constant variable that vary from 0 to 1, that is the learning rate, and d minus di into xi that we have obtained from the other mathematics. So this is how we are updating the weight matrices, by calculating the error and diminishing the error and updating the weight matrices. And this is how the learning process goes on. So from the figure we can see, so this is basically the how the feed forward and backward propagation network is working over here. So the input we have, the input we can be in various features, like if we talk about any problem, like if we talk about price forecasting, we have historical value of the prices, the associated features like generation, load, and meteorological factors. So these are the input. So once we are giving the input, there will be many hidden layers. So optimally we have to decide which hidden layer need to be given, so that our output will be designed accordingly and will be trained. So over here in this example, we have considered the two hidden layers. So each hidden layers have their own weights. So the updation that we are talking about is the weights. Initially, the weights are initialized like 0.11. The initial weights are being assigned. Once the weights are being assigned, we are be calculating the output. The output will be like that I told you at earlier point, that this is my output. During the training process, we know the output as it is the supervised learning. We will be calculating the error, this MSE that I've told you earlier. So during that MSE, we will be updating the weights through the help of learning rate, as I've discussed previous slides. So these how the updation take place, the weights update, and the learning process goes on. This is how our model learns, and model got trained, and once it got trained, we can evaluate for the new data set, or we can train it for the real data set, or for the testing part. So this is how it works. So as we know, every model have their own hyperparameters. Like if we have talked about LSTM, that upgraded version of RNN, it have many hyperparameters like number of layers, epochs, batch size, number of neurons, dropout. These dropouts and these are the hyperparameters. These have the ability to, like, if we will put these hyperparameters randomly, then it will give the desirable output, but not as per the optimal value that we are required, the error value. So in order to train our model, we need to tune it. So basically it become a problem of optimization. So over here we choose the best combination of the choices, the search space that we used to say. So we define the search space for each and every hyperparameters, like number of neurons, dropout, hidden layers, batch size. Once we have considered the search space, then we go for the model training. Then as I've told you how the model training is working, so model training will be there, and weight will be updated, the model will learn, the model evaluation will done, and it will give the best model evaluation. And this process will continue until we will get the best hyperparameter. So this whole process is known as hyperparameter tuning. The parameter which is defined in the model architecture is known as hyperparameter. So this is how we will work for hyperparameter tuning. So we have considered the proposed model over here. This proposed model, basically, we are using the LSTM model, and for it we will be tuning our parameters, the hyperparameters, like number of hidden layers, the neurons, and everything will be hyperparameter tuned by the genetic algorithm. So LSTM model we have used in our case for the short-term electricity price forecasting. So as we can see in the flow chart, the first of all we will start, and first of all the data will be collected from the SCADA data, yeah, from generation data, and meteorological data will be collected. And once we will go for data analysis, we will see that if there is any anomalies, if there is any missing data or anything like that, we will be handled over here. So all these values will be removed, and data analysis will be done effectively. Once we got the best data set, then we will go for the feature engineering. Feature engineering is basically we will go for the feature selection. So feature selection is like if we will give all the features together, then it will become a problem of overfitting. That's why we go for taking the most optimal, or the most features that are most relevant to our dependent feature, that is electricity prices. So we will be here we will be doing it with a lasso operator. So over here, the lasso operator is it is based upon L2 regularization. So this is it impose the penalties that are not important features, and it will give the not impose the penalties. This is how it works. So once we will got the optimal features, we will go for splitting our data set into two parts, like training and testing. And in training, we will be considering our model like LSTM. So once we have our model is decided, then we will create the search space of the hyperparameter. As I've told you earlier, that the hyperparameters of LSTM model can be like number of neurons, hidden layers, and these search space will be defined for it. Like number of hidden layers, we can take it from 1 to 10, and learning rate can be taken 10 to the power minus 1 to 10 to the power minus 6. So these are the basically range, the search space we can be created. Afterwards, we can go for the search. These search space will be optimized, and the optimization algorithm, the genetic algorithm is I am using over here to to tune basically the hyperparameters. So once we have trained it, once we have trained, we will create the model and training will be done. So our objective function is like we have to validate that our objective function over here, what will be that MSE, the error that will be calculating. Once the MSE error become reduces for the training process, the hyperparameters will be tuned, and and that will be a stop situation over there, and the model will receive. Once our model is tuned, our model is prepared, then we will go for the testing phase. Testing phase will be evaluating models on the test data set, or the data set that has been not seen to our model, a real data set will be seen to it, and we will evaluate our result. So this is how we are working on it. And the hyperparameters that we have obtained for LSTM layer is over here by the help of GA algorithm is like for the number of units we have 100, the loss function is mean absolute error, and the optimizer is Adam. This is how we are obtaining all these factors. So over here we have considered the case study. So as I have told you, like the features that we over here we have like time scale of 1 to 24 hours, and the type of hours is 0 and 1. 0 means like the peak is not off peak time is considered as 1, and 0 is considered as a peak time. Then the time of scale at 0 to 7 will be the days on the week. And the type of the days like weekend will be considered as 0, weekend will be considered as 1. The type of seasons 1 to 4, we have 4 seasons as we have. And the generations from the different like conventional, non-conventional, we have the load values and the forecasted value of the load. Then we have the historical actual prices. So this is our prime data set that we have taken from the Ontario market of Spanish electricity market. So data set that we have considered is retrieved from ENTSOE, that is basically the public portal of the TSO, Transmission System Operator in Spanish electricity market. And this is my data set. And in the figure, I will be picturizing how my electricity prices, the historical electricity prices varying across the month of the year. So we can clearly see that the electricity prices have a certain pattern, and it follows the same pattern, and we can see the seasonality effect as well. Like these patterns follow a same charts over there in the previous past. So this is how we can see our the case study over here. Yes. So the data pre-processing part is over here. So once we have given our data set, then it will go for the data pre-processing. As we know, we will go for the scaling. Like why it is important? It is important because it have different degree, magnitude. Suppose you take about the like generation. Generation is in megawatt, and if you take about temperature, temperature is in degree Celsius. So these have different magnitudes. So we have to keep all of these in a single magnitude. We are converting them into 0 to 1. So how we will be doing it? We will be scaling it by the help of normalization. And normalization is a scaling technique which we have converted, rescaled our each and every input in 0 to 1. So this is the formula: xi minus minimum value upon maximum minus minimum. So maximum x max and x min are the maximum and minimum value of the features respectively. And the normalization is good when the distribution does not follow the Gaussian distribution. This is how we are going for the data pre-processing stuff. So once we have pre-processed our data set, we will go for the outlier detection. As we consider the temperature, like I'm just taking an example. The temperature right now is like a 22 degrees Celsius in Jaipur. So like it suddenly now, if you collect the data set, in suddenly might be due to some mistake or due to some error, the temperature becomes 57 or 51 degrees Celsius. It is not possible looking at the climate right now. So that we consider as an outlier, might be due to the malfunctioning of the transducer, or might be anything. So these outlier need to be handled. Otherwise, it will deviate our forecasting result, and forecasting accuracy will be diminished. So how we'll be doing it? We will be doing it. First of all, we will be plotting those things. Plotting will be doing this by the IQR method, interquartile range. As we can see, there's in outliers like the values we have Q1 and Q3. Q1 indicate like 25% of data sets are within this limit, and 27% in Q3, and the middle of that there is a medium. And and this is the maximum and the minimum value are decided. The basic calculation is like maximum value will be decided like Q3 plus 1.5 into IQR range, and the minimum value that Q1 minus 1.5 into IQ range. So these values below and after this limit, minimum and the maximum value, the outliers will be considered. Now the question is how will you remove the outliers? The outliers can be removed by the various ways. We can replace the outliers by the nearby value. Suppose if we're taking an example of temperature. So temperature value, like if the temperature right now is 21 degrees Celsius, the temperature right now is that 51 degrees Celsius. That if it is coming, we will remove that, we will replace it with the nearby values, and this is how we'll do it. So this is basically a Pearson correlation plot. Over here, we will be plotting like how our associated features are having a correlation with its electricity prices, and so we can see that this is a correlation between 1 to -1. Here we're calculating the value of R, and this Pearson correlation basically tells that if there is a positive correlation, suppose if we talk about the load have a positive correlation with the prices. The load, if the load increases, the price will increase. Suppose if we talk about renewable integration, the renewable integration increases like solar irradiance solar irradiance penetration. This, if the solar penetration is increasing, the date and the price will become low. So this is how it have a positive and negative correlation. So this is how we are plotting it. So this is basically the construction of our LSTM model. Over here, as we have told you that we are converting data set into training and the testing part. So the output, this is 23 by 320. 23 is our time step. Like I have told you, like 23 previous values we have considered and 24th value we are calculating. So this is because we are going for day ahead. So we'll be calculating the next hour 24 considered, and 23 values we have considered, 24th value we will be calculating, and the batch size of 320 we have considered, and this is the parameters we have obtained. And this is how we are going for the dropout. We are removing the dropout layers. Dropout means 20% of data is being removed. Otherwise, the problem of overfitting will be there, and dropout is very necessary. And then we have given it to the dense layer, and this is how we are going for it. So hyperparameter tuning by the GA algorithm, we have, as we have discussed, the search space that I'm talking about earlier in the slides. The search space, we have a search space from number of layers of 2 to 6, and the times and the step size is 1, and number of units we are considering 32 to 512. So these are, and the learning rate 10 to the power -3 to 10 to the power -1, and with the step size of 10 to the power -1. So this is basically the search space. Our GA will be looking for the hyperparameters in these boundaries, and once it will tune it with a with an objective function of MSE, we will be getting the best hyperparameters, and that will be number of layers will be 3. The number of units will be 320, 320, 160. As it have 3 layers, the number of units of each layers we are talking about. First layer will have 320 units, and another 320, and third one will be having 160, and the learning rate of 0.001. That is the optimal hyperparameters that we have construct for the LSTM model by GA. So this is my result section. Over here, we will be calculating our proposed model, that is GA-LSTM, with respect to the other benchmark models, like we have calculated with LSTM and other gradient boosting and random forest and linear regression models. And we have plotted these figures. And on the right side, we have plotted all the figures with respect to our actual and the proposed model. And it found that like our actual prices will follow that our proposed model follows the actual prices very closely, and it gave a good prediction. Now we will be considering solar radiance forecasting, and now the domain expertise goes with our supervisor, ma'am, Dr. Prinajan ma'am. Now she will uh, deliver the lecture over here.
So, is my voice audible?
Yes, ma'am.
Audible, I guess. Right. So here, let us start with solar irradiance forecasting. Now, in solar radiance forecasting, what our input from our side is, so it's a power per unit area received from the sun in the form of electromagnetic radiation as measured in the wavelength range of the measuring instrument. The solar radiance is measured in watts per square meter in SI units. Solar irradiance forecasting is used to make predictions of full irradiance value based on past and present relevant data. So types of forecasting: short term and long term. So short term is forecasting up to 7 days ahead. It's valuable for grid operators to make decisions of grid operation as well as for electricity market operators. Long term solar forecasting is forecasting annually or monthly, and it is useful for uh, energy producers in negotiating contracts with financial entities and utilities uh, that have distribute the generated energy. In this lecture, we will discuss the ensemble learning technique of machine learning for solar irradiance forecasting. So, ensemble technique is a machine learning paradigm with where multiple models, often called weak learners, are trained to solve the same problem and combine to get better results. So, the training samples they are divided into data sets, sample 1, sample 2, up to sample n. And then on each data set, regression algorithm is used. So regression algorithm 1, 2, up to regression algorithm n. And all the results are aggregated, and then we have the final prediction. This is ensemble technique. Light GBM is a gradient boosting framework which is used here, which is based on the decision tree technique used for ranking, classification, and variety of other machine learning applications. So as you can see here, this is a case study. So it's a meteorological data set consists of hourly average weather conditions for 3 years. Solar irradiance data from National Renewable Energy Laboratory 23. So table 3, it's a parameters with the description of meteorological data set. So it's temperature, relative humidity, pressure, wind speed, wind direction, rainfall, short-term solar irradiance, cloud opacity, and zenith. The descriptions are given. And we have the mean solar irradiance for each month. Results. To evaluate the proposed model's performance, a comparative analysis was conducted with other benchmark models as the light gradient boosting machine model, light GBM, that not only takes less computational time but also improves the forecasting performance. So, among all the benchmark model, light GBM model has the lowest error matrix uh, for the data set which we used, and best R square R loss, R square R score. So, you have the model, and the table shows ME, RMSE, R square, RMSLE, and MEP error coefficients. So you have the light gradient boosting machine giving shown in the first line, and the other ensemble models are shown below. So the conclusion of this, which we have discussed, uh, electricity price forecasting and solar radiance forecasting. So basically, deep learning model or advanced machine learning models which are opted for electricity price forecasting or solar radiance forecasting or any other renewable source of forecasting are good as they have unique capability of handling complex and volatile nature. Along with that, it can handle long and short-term dependencies as well. Other new advanced models like Transformer or Mamba or CNN LSTM are can be used for your data set to identify their accuracy in comparison to other benchmark models. So now let us talk about blockchain. So blockchain is a decentralized and distributed ledger technology that records transactions across a network of computers. It operates without a central authority, making it inherently secure and resistant to tampering. So this is here how a blockchain works. So as we can see in the figure, if A wants to send money to B, the transaction is represented online as a block. The block is broadcast to every party in the network, and after that, those in the network approve the transaction is valid. The block then can be added to the chain, which provides an indelible and transparent record of transactions. The money moves from A to B. So, blockchain technology offers a secure and transparent way to record energy transactions. Energy trading plays a crucial role in optimizing energy distribution and ensuring a stable supply. So, this is what application of blockchain for energy trading we are talking about. The adoption of blockchain in energy trading promises several significant advantages, including enhanced transparency, reduced fraud, lower operational cost, and the potential for peer-to-peer energy exchanges. Then we have overview of energy trading. So uh, we have discussed many times in energy trading, and in energy trading, the important point is multiple parties are involved in buying and selling energy, leading to a centralized and complex system. So challenges. So lack of transparencies. The traditional energy trading system lacks transparency, making it difficult for consumers to understand the source and pricing of their energy. Um, High transaction costs, the involvement of multiple intermediaries result in high transaction cost, which can be a barrier to entry for new market players. Market manipulation. Centralized systems are vulnerable to market manipulation and fraud. Limited accessibility. Traditional energy trading is often inaccessible to smaller producers and consumers. Slow settlements. Settlement can take days or even weeks to process, causing delays in payments and financial inefficiencies. So, blockchain technology addresses many of these challenges, providing a more transparent, efficient, and accessible way to trade energy. So, for more broader applications, peer-to-peer energy trading. So, blockchain technology is transforming the energy industry by enabling peer-to-peer energy trading, that is, from consumer to consumer energy trading. This or prosumer to prosumer energy trading. This allows individual and businesses to buy and sell energy directly with each other, bypassing traditional energy providers and creating a more efficient and sustainable energy market. Another is tokenization of energy assets. Tokenization of energy assets is a process of converting energy assets such as solar panels or wind turbines into digital tokens that can be traded on blockchain based platforms. This allows for easy and efficient trading of renewable energy assets and enables individuals and organizations to invest in renewable energy projects. Another is grid management and blockchain. Blockchain can be used to create smart grids that are more efficient and secure. Smart grids can help to manage energy distribution and prevent blackouts and reduce energy waste. Carbon credit and emission reduction. Blockchain technology can play a crucial role in reducing carbon emissions and promoting sustainability. By tokenizing carbon credits, we can create a transparent and secure marketplace for trading these assets. This incentivizes companies to reduce their carbon footprint and rewards those who have already done so. These benefits illustrate how blockchain technology is revolutionizing energy trading, making it more transparent, secure, efficient, and accessible to a broader range of participants. Now, after this, a small overview of blockchain technology and applications to energy trading, energy markets, and other areas, grid management. I am asking the PhD scholar Ashish, to explain you one example of forecasting on Python platform, right? So let's go to that.
Thank you, ma'am, for the overview of application of AI in power system and the blockchain application. Now, in this we will be delivering a hands-on session, like how we will be implementing the LSTM model for our problem of electricity price forecasting. So let's see, like these are the basic libraries like NumPy, Pandas, Matplot, and sklearn libraries for MinPy. And these basically libraries are the invent libraries which are in the Python. So over here, I am be implementing this in the Python in Notepad, in and Jupyter Notebook. Sorry. So these are my libraries. Once I have run my libraries, then I will go for like I will be reading my data set, that is electricity price data set, and I have plotted and I have shown them like df.1.head. In this, we can see the how the time we have with the data set is in hourly form, the resolution is hourly form, and it have a generation, it have a generation from conventional, non-conventional, load, and other meteorological factors, wind speed, load is over there, and the historical value of electricity prices. So this is basically the head of my data set. Once I have done my data set, I will check the missing values. I will go for the data pre-processing. Over here, we can clearly see that we are checking the duplicates values. If there is the duplicates values, that data are repeated, then we will be summarizing them and replacing them. Then we will go for like we will calculating the missing values. Like if there is null values, df dot is dot null. If these values are there, then these values will be replaced, and with so this is how we are dealing with data pre-processing values. So after that, we will be going for like once we have seen that there is no missing values and there is nothing like that, or if there is any rows that is equal to 0, we will remove that rows. Yeah, interpolate it with bifill nearby values. We will interpolate it. Once it is being done, we will see how our data set is, and our data set is now the clean one, and we have done everything that is required in the data pre-processing stuff. So once we have done, we are checking the what are the data types of each and every input we have. So each and every input data we have 19 inputs we have, and for the 19 inputs, the data type is plot 32. So this is how my data set look like and my data type are. So over here, I will be calculating the correlation plot. Correlation plot, basically, I will be looking for like my dependent variable is electricity prices, and how my electricity prices is dependent on like other attribute features. Like we can clearly see that the generation from the coal have a correlation of 0.47. The load forecast have a 0.47, and the negative for the wind and shore and nuclear. So it is like how it is correlating with this. So this is my like correlation plot, correlation indices. So once we have seen this, then we will be seeing that what are the most important and relevant. Uh, then we will see the one of the most important, like we will see the magnitude of the correlation. We will calculate the ABS, np dot ABS. For here we will calculating the this magnitude we are calculating, and the plus minus will be considered, and we will seeing that the threshold of 0.2, and according to that we are come across these are my features, and other features are eliminated because their features are not so much important for our price. uh, so this is how we are doing it, and now we can see the trend. So we have plotted the trend part. I have checked the seasonality. I have checked the result. So trend means this is how our trend it all throughout the year. and my seasons, that it is showing that my seasons are like repeating. It means it have a seasonality, and my residuals are like this. So once we have gone for this data preprocessing stuff, then we will go for the feature selection. As I have told you in the earlier slides, that we are going for the lasso operator. The lasso operator is utilized to go for the to select the most optimal features. So over here, by this lasso operator, like we are fitting the values, splitting the values in point with a data split of point two. Once we have splitted it, then the fit function will be executed and the fit transformation, and we will see the which features are more important and their importance as compared to our historical electricity prices. So this is basically the graph, and we found that these are the five parameters that have a high importance to our historical electricity prices they had. So once we have gone through those prices, we will we will draw the head of this. So we have drawn the head. Head means like we are seeing the first five values. So once we have drawn the head, we will calculate. We will plot. I have plot my price in year on month-wise basis for different years. So this is my plot for it. Now, once we have gone for this, gone for missing values, and gone for the data pre-processing stuff by feature selection, by lasso operator, we will go towards like outlier detection. First, we will plot the all my features over here in the box plot. In box plot, we can clearly see that in generation fossil there are outlets. Many outlets are there over here, and other outlets are over here. So these outliers are need to be replaced. So I am replacing these outlets by the medium value. So this is, you can see that df dot column less than down bound, and this is the down bound. If you'll see, this is the maximum value, this is the minimum value. And if it is less than this, and if it is greater than the upper bound, then it will be replaced by the medium value. So once we have replaced all things, then this is my data set, and we have drawn it, and this is the values we got it. So once we have gone for the box plot and everything, we have drawn the correlation plot, the heat map. Basically, I have drawn for all the features, and that establishes that how my actual prices is correlating with the associated features. Once we have drawn this, we will go for we have our data set. Now we have gone for feature selection and everything has been done. Now we are splitting it in two portions. It basically for training and the testing part. The training part, as it have 35,000 values, so 80% values are kept in like training portion. So training portion have 80%, 35,000, 28051. So we'll be before these 280 28,051 values are in the training portion, and the remaining were in the testing portion. So once we have recovered these things, then we will go for we will go for reshaping our array, as we cannot give the actual values everything in our data set just like this only. We have to reshape it in these are my value 28,027, and 24 is the time step, and 20 are the features. So this is how we are going for reshaping it. Before, without it, it will not be executed. So once we have reshaped our data set, we are giving it to our LST model. So this is basically our LST model look like. So over here we are from Keras library we have installed. So in Keras library we are taking the sequential, dense, and LSTM dropout. So in sequential, we can see it is a sequential model, and we have added the LSTM layer. LSTM layer unit we have considered 75. That is the optimal value which we have received earlier. So 75, and the training shape is over there like X train and X train. So and the dropout is being implemented over there. The 20% means the whole data set, 20% data set will be removed and will be done and executed again, and then it passed to the dense set. This is done because if we have to remove the problem of overfitting, that the model will not learn each and every point. So we will keep hiding our certain data sets so that our model will not go for the problem of overfitting. So once we have done this, we will go for model fit. We will be running our model for 20 bucks. For we have we are running our model for 20 bucks just for a case study only. Otherwise, we have to go for more than 100. Yeah, 150. So once we have fit our model for these values, for the batch size of 72 NBPs and everything like this, then the training process goes on. Once it is being obtained, our model, we can obtain the predicted values. How can we obtain the predicted values? Like by using the extend value into our model, and then it will give the white test. White test actually is the predictions. So once we have received this y value, we will save it in predicted prices in our data set. So this is how we are plotting our values, the test data set and the predicted values, the actual and the predicted values, and we can clearly see our LSTM model is clearly following the test data set, the actual prices, and this is my we are calculating the RMSE and this and these values, and this is how we are doing it. We have calculated over here the RMSs and everything. So basically, in this hands-on, we can clearly see how we are taking our data set, how we are making it compatible for our LSTM model by rescaling it into three-dimensional, and we are how we are fitting it, and this is how we are able to do it. This is it in implementation of LSTM for electricity price forecasting data set. Thank you.
This is the end of our discussion on AI applications to power system. And I request the participants to please ask the questions, if any. Yes, my speaker was off. If anyone interested may ask the questions. There is one question. Why are we not using LSTM RNN to predict solar irradiance? Is there a particular reason like nature of the data set? How you choose the right method to forecast from a given data set? On what factors the choice of forecasting method depends? Ashish, please answer.
Okay, thank you. So basically, we are as we have discussed that RNN is the like recurrent neural network, and the upgraded version of RNN is LSTM. So LSTM is these two models are basically a temporal and sequential forecasting models, time series forecasting model, and both model are if both model have the same nature of working, but the RNN have their own limitations. That's why we are going for LSTM, as LSTM is the upgraded version of RNN. So if we will combine them LSTM and RNN all together, then it might be like the results will not be so much effective, because both the nature of the LSTM RNN is this hybrid model is work for the forecasting the time series problem. So if we will combine RNN, we will be carrying forward the problems of RNN with LSTM. So might not be fruitful. And rather than this, we can use LSTM for the better prediction.
Any other question, please? I hope you are benefited with the content which we have shared with you in this uh, presentation. Now we will move forward to our next discussion or next lecture. Are my slides visible?
Yes, ma'am.
Okay, thank you. So here we are going to discuss about security constraint unit commitment considering renewable and storage integration. So throughout this course, you must have studied about OPF, optimal power flow, economic load dispatch, and in last class we did market-based economic dispatch, as far as I know about my content. So here, what is security constraint unit commitment? It is a largely used and a very important algorithm for efficient operation of a grid. And we are going to discuss about when we integrate renewable and storage, how the equations are modified. So this is the introduction. So in the worldwide electricity sector has been transformed to open market structure with the aim of improving system efficiency and benefits to customers. So a lot of discussion, I think, in your this FDP has been done. So let us move forward. I believe that you know what is open market structure and how it improves the system efficiency and how it is beneficial to customers. These two things are independent of each other: system efficiency and benefits to customers. Then here, when the system is restructured, you have different entities handling generation, transmission, distribution companies, independent system operator, and market operator and power exchange. Each one of them have their own operation and they are independent of each other. But system operator is independent, it is not profit oriented, and it works to manage the whole system. So the fundamental task of power system is to serve electricity demand reliably, and security constraint UC and ED are the prominent power system operation algorithms. Now, conventional UC schedule thermal generators to maximize operating cost over a short period of time, subject to system constraints such as load balance, spinning reserve, minimum up down times, generator limits, and emission constraints. How these are conducted in deregulated structure, which we will be understanding, and how SCUC is developed in a deregulated structure. So this is earlier structure of electricity utility, vertically integrated utility. It was completely handled by single utility, generation, transmission, distribution, and consumers were separate. This is the second model, and this is the third model, but then this is the wholesale market model, which after Electricity Act 2003, it was adopted in India. So you have generation companies coming into the wholesale market, you have distribution companies also coming into the wholesale market for buying the power, generation companies selling the power, and you have the consumers. And the wholesale market is operated and managed by ISO, TSO, and MO. So primarily, market operator has a job of managing wholesale market, and system operator manages the whole system. Gencos, wholesale market, distribution company, and consumers. They do not manage the wholesale market, but they manage the flow of electricity from gen to distribution company to customers to consumers using based on the rules of reliable flow of power on the transmission lines, based on the minimum operating cost. This is done by system operator. See, market operator is only concerned about operation of market. So it gives a platform to generation company and distribution company or retailers to actually compete there and save their market share and have their demand satisfied at minimum cost. So this is a retail market competition. This is a function of vertically integrated monopoly utility. I'm just moving fast on these slides because you have all read about it, and we will be focusing more on SCUC. So vertically integrated was a monopoly utility. Then after unbundling or restructuring, we have these actors: Genco, Disco, market operator, ISO, and Transco. So this is the operation of generating companies now own the power plants, operate the power plants, compete with each other to sell the energy, and have the competitive advantages like more efficient plants, cheaper fuels, and high plant availability. And the major important benefit of deregulation is that generating companies do not have any obligation to supply power. Their mode of operation is profit based rather than cost based. Earlier it was cost based, but now it is a profit based. So distribution companies own and operate the distribution networks. They regulate business revenues determined by the regulator based on the values of the asset. Monopoly for the sale of electricity in their territory when there is no retail market. Retailers, they buy electrical energy from generators. They sell electrical energy to consumers. They do not own large physical assets, often owned by a generator or a distribution company. Competitive advantages are negotiate good price with generators, identification of good customers, efficient billing system. Market operator, just like Indian Energy Exchange, Power Exchange India Limited in India, they facilitate trading of electricity, match the bids and offers submitted by buyers and sellers of electrical energy. They run the market settlement system. What are the requirements of a market operator? Fairness and independence, efficient technology to support trading, efficient settlement of trades. Then independent system operator. So independent system operator, we are going to focus on independent system operator because it is the entity who runs SCUC, Security Constraint Unit Commitment. It operates the power system. It maintained load and generation balance. Now, generation company is not worried about this load and generation balance. Distribution companies coming with the load, it is not worried about load and generation balance. Who is worried? System operator. Because if there is imbalance in load and generation, it affects the system. You have voltage fluctuations and frequency fluctuations. So responsible for operational reliability, independent system operator, and it operates the market of last resort. So market of last resort. So market operator runs day-ahead electricity market and hour-ahead or intraday markets. But real-time market, which is the closest to the time of supply, is run by system operator to do the final balance of load and generation and to also focus on the spinning reserve requirements. It must be independent from other participants to ensure fairness of market, right? It must be independent from other participants. It should be non-profit oriented. That is, they and owns only computing and communication assets. They do not own the grid. They do so in coordination with the grid. Please wait. Yes, meet me after 4 p.m. So you also known as regional transmission organizations. So transmission companies, they own and maintain transmission assets. They have lines, substations, and DC lines. They operate these assets as instructed by ISO. So ISO and transmission company. So you can say POSOCO, which is the grid operator of India now, in with PGCIL, they work together. Operate these assets as instructed by ISO. Regulated business. Revenues determined by the regulator based on the value of the assets. Transmission system operator. In transmission companies, and now you have transmission system operator. So you had ISO, transmission companies, and now transmission system operator. So transmission system operator, in some countries you have transmission system operator. It it does the role of transmission company plus independent system operator together. So Europe has TSO, North America has ISO or RTOs. So you have large consumers, industrial or large commercial consumers may buy directly from the electricity market, may buy electricity at time varying prices, can sell demand response. These are large consumers. Then you have small consumers, small consumers. So typically rebundling. So first it was unbundling, now a kind of rebundling is may also exist. Distribution plus retail, generation transmission network owner, generation and retail system operator and market operator like CISO, California ISO, and transmission owner and distribution owner. So perspectives. Old model point of view of the vertically integrated utility is only one that matters. New model, each actor has a different perspective because its motivation is different. How does it make money? Different ways of looking at the same problem. Now, old model had only one. It was an obligation to supply energy, and its objective was cost based. New model, each actor cost based means minimize cost, and they could not worry about profit because they had the obligation, they had to supply power. New model, supplying of power is a choice, and each actor has a different perspective because its motivation is different. Now, role of system operator. So now going deeply into the role of system operator, it has a responsibility of ensuring system security and reliability, fair and equitable transmission tariffs, providing for other system services. So major responsibility of system is to ensure security and reliability. The difference between security and reliability, they are somewhat intermingled and they are different on uh, a bit also. So reliability is maintaining demand supply balance with maximum efficiency. You cannot say 100% efficiency, but maximum efficiency. And security is whenever any big contingency happens in the system, keeps the system running and keeps supplying the load without any major outages. So this is security. So with different market structures evolving in various countries, system operator can be placed in two categories. System operator in pool market and system operator in bilateral market. Now, pool market is a market which is run by market operator, and there the trading between generation and distribution, Genco and distribution companies takes place. Genco come with their power and bid offer, and distribution companies come with their bid with their demand. And since considering electricity as a homogeneous commodity, electricity as a commodity, the market clearing price is identified, and all the Gencos are paid at that market clearing price, those who are able to ensure their market share, and it only depends upon how much price they have bid. A system operator in pool market. So it is now in pool market, what is the role of system operator? Now this is when the system operator is working in together with market operator. So they are responsible for market settlement. If they are not working together, MO will do the market settlement, and the information will be provided to system operator about the generation companies who have been selected to supply the demand and about the distribution companies whose demand will be fulfilled. Excuse me, after 4 week class children. So you have responsible for market settlement, unit commitment, pool price determination, responsible for pool market administration. This is also when you are in together with market operator in a pool market structure. Responsible for system security and control, procuring necessary ancillary services. In bilateral market, when bilateral market is forward markets, where there is a trading between one-to-one trading So here the bulk of the energy transactions are carried out as bilateral trades, while there may also exist a day-ahead spot market, not responsible for market administration, generation scheduling or dispatch function. Market administration is carried out by separate entity, power exchange or MO, and participation in the market is not mandatory. Responsible for system security and control, procuring necessary ancillary services. Now here, when there is a bilateral market, so when bilateral market is existing and you have a hybrid market where you have bilateral as well as pool market option, in that case, the most beneficial model is to separate system operator from with the functionaries of the market operator, and completely market administration is done by MO. System operator only does the system security and control, and they procure necessary ancillary services. All the information of bilateral trade must be submitted to system operator. All the information about the spot market rate must be submitted to the system operator, and after that they determine for all the trading done, for all the future transmission of power based on the trading done, how secure the system is, and how much ancillary services are required. And then they do the necessary ancillary service procurement. In both the types of market structure, the primary responsibility of system operator is to maintain system security and undertake congestion management, for which it has to procure ancillary services and also decide on the various control actions to be taken. In pool type, it also does the market settlement for suppliers and consumer goods. So this role of system operator in pool type carries out load forecast to determine the aggregate hourly load demand in its system the next day, receives bids for supply of power from GENCOs. The bids can be of different types and may sometimes also include information on unit commitments such as startup time, shutdown time, ramp rate limits, and associated cost. Based on this information, it simulates the hourly dispatch using a model similar to the UC model and evaluates the system price for each hour of the next day, formulates the nodal marginal cost and congestion transmission price based on the system price. In real time, that is the market of the last resort, it dispatches generation and load, procures and provides system services such as reactive power support, frequency regulation, and other ancillary services. After real time, calculates the settlements, nodal prices of energy and transmission congestion surcharges. Settlements include marginal fuel cost, capacity cost, startup costs, congestion transmission charges, network service charges, and ancillary service payments. When you come to bilateral structure, the rule. SO is informed for all hour-to-hour transactions that are to take place the next day, either by the market operator or power exchange based on the bidding mechanism, as in the hourly spot market in Node 2, or through bilateral contract between the GENCO and the customer based on independent negotiations. After that, it carried out security constraint unit commitment based on its load forecast for the next day, availability of transmission capacity, and other factors to determine the level of system security. If required, it makes provision for additional transmission capacity, ancillary services, and orders curtailment of certain transactions. In real time, monitors system for power flows, frequency, and voltage conditions and trades. Interacts with the regional networks, control rooms for providing adequate frequency regulation services, reactive support, and voltage control services. Power imbalances are corrected by making provision for parties which shall be responsible for this and charge the same to the defaulting parties. After real time settlement of the accounts and payments of the ancillary services providers. Now, here, when it is in the pool market, so what is happening in the pool market? Here, when we talk about SO in the pool type, we are not allowing bilateral contracts. It is a system where bilateral contracts are not there. So all the trading takes place in pool market. So when the system operator, in such a system operator works in coordination with the market operator and does all these job. Now here, when it does all this job, you can see here in the third line that they accept the bids of different types, which may include unit commitment information such as startup time, shutdown time, ramp rate limits, and associated cost. This is called a centralized trading where market price is identified by a unit commitment program where the bids of all the generation companies are in the form of uh, their cost curve, their cost coefficients, this all their characteristics are submitted rather than a price bid. So the characteristics of all the gencos who are participating in the market are taken, and the demand is taken. And when the UC is run, the all the generators which are able to supply that demand in minimum cost are selected, right? This is of course the answer of the UC. It selects the generators which supply the power with the minimum cost. So the generation companies which are able to supply that power in the minimum cost are selected, and the demand which is fulfilled is also finalized. Now here in the coming slides, we will see how this UC is able to identify the market price as well. The same. When you come to a structure where you have bilateral contracts and you have the pool market running together, then pool market is handled by market operator and price is identified using market settlement. Then bilateral contracts are also existing. The information of the pool market trading and the bilateral contracts are submitted to the system operator, and then system operator does the UC, and that is called security constraint unit commitment. Earlier also, this is also security constraint unit commitment if you take the security constraints into account. So this is security constraint unit commitment. You take the N-1 line contingency criteria and all the line flow limits criteria, DCOPF or ACOPF, you include in the UC, and that becomes the SCUC. Now here, what is the final authority of system operator? After it carried out UC based on its load forecast for the next day, availability of transmission capacity and other factors to determine the level of system security. If required, it makes provision for additional transmission capacity. If it finds out that you need additional transmission capacity to meet the security level, it may also buy ancillary services to enhance, to support the security level, or it may order definitely curtailment of certain transactions which have been selected in electricity, market, or which are existing bilateral contracts. But certain curtailment may be ordered because their location on the grid is such that they are creating a lots of security issues and line congestion as well. So this SCUC is the final thing which can do uh, these actions. So in real time, when the system is running, it monitors the power flows, frequency, and voltage conditions, and trades. So this is centralized trading using unit commitment program. And this, which I said, this is when you are not having bilateral contracts. So you have a unit commitment program. Either you have the bids from the distribution companies or you forecast the load. Both the models exist. That is a market settlement where you do not allow distribution companies to give the bids, only the load forecast is taken, or you allow the distribution companies to give the bids. So both are can be done. And then you have generator bids. Both are input to the unit commitment program. The final answer is minimum cost schedule, which actually selects those generators which are able to supply this load forecast at the minimum cost. And after that, the market price is identified. So how the market price is identified? Let's see. So generator bids, all the units are bid separately. Components, piecewise linear marginal price curve. These are the components of the bid. Uh, these are not simple quantity price bids. These are this kind of bids. So all units are bid separately. Components, piecewise linear marginal price curve, startup price, And parameters: minimum megawatt, maximum megawatt, minimum uptime, minimum downtime. Everything about the generators are the part of these bids. These bids do not reflect the cost. Bidding very low to get in schedule is allowed, but these bids do not reflect the cost. Load forecast. So load is usually treated as a passive market participant. Assume that there is no demand response to prices. Then generator schedule is identified. So after running the UC, the units which are able to supply the demand at the minimum cost are identified, and then their generation schedule is also identified. And this UC is not a simple UC. It consists of line flow limits and N-1 line contingency criteria, wind integration, and everything. So you have uh, this program running, and you get the generation schedule. So when you get the generation schedule, you have the units and how much they will be supplying. So looking at the units to identify the price in every hour, most expensive unit needed to meet the load at each period is identified, and its marginal cost of generation, or its variable cost, is the market clearing price. This statement goes in line with those who know the market clearing process, where the costliest of the unit becomes the marginal units, and its marginal cost of generation makes the market clearing price. So this is how, after running UC, you identify market clearing price. So here market clearing price has been merged with the UC. So what is the market price? You bid from margin units, sets the market clearing price at each period. This is called system marginal price. All energy traded through pool during that period is bought and sold at that price. So this is the problem formulation of that UC. So here you have CIPIT. This is the cost of generation of the ith generating unit, and the cost curve is provided by the generating unit, and this is the startup cost of that generating unit. This is the load generation balance constraint. You have generating limit constraints, you have ramp rate limit constraints, you have minimum uptime constraints, minimum downtime constraints. So this is a kind of your optimization problem. And here, the if you use the transmission line constraints and line flow limit constraints, and if you merge a DC OPF with this, it becomes security constraint unit commitment, and actually it is run like that. And then you become a centralized. So this kind of you identify the market price by having the generators in the by putting the generators in the ascending order of their marginal cost of generation, and the most costly generator makes the becomes the marginal generator, and its marginal cost of generation is the market clearing price. So that is centralized trading, where you have only pool and where you do not have bilateral contracts, and where you have both, so that becomes bilateral trading, and this is the comparison. So security constraint unit commitment. Uh, Earlier problem was also run by system operator, which because in the centralized kind of trading, in bilateral kind of trading, considering renewable energy, this is what I'm going to discuss now. So conventional UC problem: schedule thermal units to maximize operating cost over a short period of time, subjected to system constraints such as load balance, spinning reserve, minimum uptime, downtime, generator limits, and emission constraints. This would not assure the sufficient power flow from generation load due to indeterminate network constraints in traditional UC problem. That is, you have to take into account network constraints, and network constraints are line flow limit constraints. This problem can be mitigated by incorporating network constraint in UC formulation, and this is called security constraint UC, which I have told you. Now, two terms are used: adequacy and security. So what is adequacy? There must be an appropriate quantity of capability resources available to satisfy the maximum requirement. And security, the system must be prepared to resist any system line contingency, keeping the system parameters and limits. So the two things, adequacy and security. Adequacy is also is equivalent to reliability, or it is, sometimes both of them are often on they are used in their own place, used in each other's place. So this is, you must have appropriate quantity of capability resources to satisfy the maximum requirement. And security, the system must be prepared to resist any system line contingency, keeping the system parameters in limit, that is voltage and frequency. SCUC program which can handle the system contingency securely is SCUC in true sense. So three elements are included in SCUC paradigm: supplying the load, maximizing security, and minimizing the cost. SCUC is different from that of regulated industry since the ISO would have no control over the generation bits submitted by GenCos. Now, network contingency affect the network constraints calculation under N-1 criteria. So when we say N-1 criteria, where N is a number of components. So when we say N-1 line contingency criteria, so N is a number of line and -1 is that out of the available N lines, one line has gone, has been, is under outage. Now that one line is a very critical line because that line has a capacity to flow maximum power. So when that line is under outage, then it is a major line contingency. And under this line contingency, how efficient our system is to supply the load without the parameters going out of range. So that needs to be secured, and that is secured at the time of unit commitment only. So such units are selected which have sufficient spinning reserve, which satisfy the spinning reserve requirement. Such units are selected which have good ramp capability, so that if, and their location also is such that if major line contingency happens, they are able to supply the load without any load curtailment. They are able to supply the load without parameters going out of range. Of course, what is the major objective of UC? The major objective of UC the major objective of UC major objective of UC is to schedule the power with minimum cost criteria. But here when you go for SCUC, it has two objectives now: manage the security plus at minimum cost, and both of these objectives are contradictory. So a trade-off is identified between the cost and the security. So furthermore, DC network constraints are more relevant for solving stochastic SUC with N-1 line contingency to ensure system security. So one of the factors, injection sensitivity factors, are generally used for expressing DC power flow equations because it requires reduced number of variables. So lesser the variables, lesser the computational requirement. So primary limitation lies in the N-1 contingency criteria, where it needs high number of coefficients to simulate power flow in contingency state. This results into huge models having high computation requirement. Now, when you have renewable integration, so when you have the renewable integration and which is increasing, so environmental concerns and reduction in dependency on fossil fuels provided abundant chance for renewable energy resources like wind to meet the ever increasing load. Large integration of intermittent wind generation increases reliability issues and system security issues as well. Reliability and adequacy are one and the same thing. The system operator to maintain grid operations. A feasible solution provides optimal generation scheduling with an estimate of required megawatt capacity reserve for handling wind intermittency and inevitable contingency. So, what is a feasible solution? It provides optimal generator scheduling with an estimate of required megawatt capacity reserve. Reserve is necessary for handling wind intermittency and inevitable contingency. Reserve can be provided by fast acting generators and energy storage systems. Fast acting generators, which have very small ramp and uh, not ramp, like they can be, they can be made on very fast, and energy storage systems they can provide. Now, fast acting generators are being discouraged due to emphasis on carbon free technology. Fast acting generators are diesel and oil, so they are discouraged due to emphasis on carbon free technology. So, ESS can absorb the surplus of renewable energy and supply during deficit to mitigate demand supply unbalance. This enhances the operational feasibility, flexibility of the system. So wind uncertainty is a primarily modeled. So just leave this. So we have let us take CAES as energy storage for large wind integration and develop our security constraint unit commitment algorithm. So CAES is actually a very good energy storage in comparison to battery energy storage, where you have large wind integration, and when you go to transmission lines, you have large bulk wind integration. And CAES, the rating power range of CAES as bulk ESS technology is 2 to 2500 megawatt. So this is the problem formulation with CAES. Now, stochastic SCUC is mathematically, now why do we call it stochastic? Because we are having wind integration. And when we have the wind integration, we need to handle the uncertainty. So to handle the uncertainty of wind integration, which means that our algorithm should be robust enough to uh, absorb the uncertainty of expected uncertainty of the renewable integration. So whenever, since this is an operational problem, we run the algorithm before the actual day and we find out the scheduling for the next 24 hours of the next day. So we have input as the forecasted load and the forecasted renewable generation. Both of them have uncertainty. That is, they are not actual. Whatever we have forecasted may be different from the actual. Now we need to handle this uncertainty and make our algorithm as robust as possible. So what do we do is, which is a general method which is used, is you to handle the uncertainty, you go for the Monte Carlo simulations. So what is Monte Carlo simulations? Monte Carlo simulation says that for a given forecasted wind generation and for and the forecasted uh, uncertainty parameters of the wind generation, generate the scenarios. Now, generally, it is first our job is to identify what is the probability distribution function of the wind generation subjected based on its variability and uncertainty. In most of the problems which we handle in research, we use normal distribution as the representation of the uncertainty of wind generation or load generation. In the normal distribution, we have a mean and a standard deviation. What normal distribution says is that for a given mean and the standard deviation, the wind is subjected to following this normal distribution. So the output, the actual wind output can be any of the values on the normal distribution curve. So Monte Carlo simulation says, and of course, the normal distribution has the probability also. So as if you're very closer to the forecasted value, which forms the mean value of the normal distribution, higher is the probability. And as you move far from the higher is the probability of their uh, coming of the wind output. And as you move away from the mean value, the probability reduces. This you all can imagine, like you know what how the normal distribution curve looks like. So Monte Carlo simulation says based on the given normal probability distribution function of the wind generation in any given geographical area, our job is to first generate as many as possible feasible wind wind output depending upon the normal distribution. So and all these are called scenarios of the wind generation. And for large number of scenarios of the wind generation, our SCUC problem is solved, and finally we find the expected SCUC solution, right? This is one of the most common way of handling the uncertainty of wind generation, or uncertainty of load for that matter. Now, this algorithm, which is being shown here, it is the capital S is the index of the scenario, and is the total number of scenarios, and small s is the index of the scenario. Pi s means that you are multiplying the probability of scenario S, and then you are doing summation over all the scenarios. This is how Monte Carlo simulation helps. Monte Carlo method and using Monte Carlo simulations helps in making this whole UC problem stochastic. Now, for any given scenario of the wind output, for all the time for all the time periods where total time periods is capital T and where small t is the index of the time, these are the various terms of the SUC problem. So first is the cost of generation of output from a thermal generator, the startup cost of the thermal generator, the shutdown cost of the thermal generator, and this K is the this K is your energy storage unit, right? This VOLL LS. So LS is the load, and load shedding. Whatever load shedding we need to do, we may need to curtail the load, and VOLL is the value of loss of load. So it is given. So the VOLL is the importance given to the load shedding. Then this is the wind generation which is curtailed, and WCP is the weight given to the power wind generation which is curtailed. And then this factor is taking into account the line flow limits, and then they are saying that this is the iota change in the line flow is minimized. So LF is a factor which actually needs to be minimized to enhance the line flow in any line. So how it is calculated, we will see. So here you can see here that this whole are summed together, and then they are minimized for every uh, wind scenario S multiplied by pi s. So what are we minimizing? We are minimizing the thermal generation cost, startup and shutdown cost. We are minimizing this cost of uh, your storage unit. We are minimizing the load curtailment. We are minimizing the wind power curtailed, and we are also minimizing the LF factor. So other equations, these are the constraints which are subjected to. So spinning reserve constraint, they say that the spinning reserve from thermal units and from the uh, your K units, which are your storages, should be greater than equal to system spinning reserve demand at time T. And these are the part of the major constraint this. Then uptime and downtime constraints of the thermal units. Then power balance constraints, which says that output power from the thermal unit plus output power from the wind unit, that is wind injected into the grid, plus output power from the storage unit, which is minus the power taken by the storage units for charging should be equal to the demand plus one factor LPF and minus load shedding. So LPF factor is uh, based on your line contingency criteria. So these are line power flow constraints. So LF is a line power flow, and this is how it is calculated. This is pre-contingency and this is post-contingency. Both are taken into account. And then line flow power is LF is calculated. And this LF is used here. Change in the LF, change in the line flow power. So this is the CAES model. Uh, so these are the charging and discharging equations and different equations of CAES model. This is one in uncertainty characterizations where we do the uncertainty modeling with using Monte Carlo simulations. So Monte Carlo simulations are nothing but the feasible values of the wind which may be injected, which may be the output of the wind generators which are in the IEEE system which we have used. So scenario generation and reduction, this is one of the methods of generating scenarios used in Monte Carlo simulations. Wind uncertainty modeling, 1,000 scenarios are generated for each hour of the next 24 hours. From 1,000, the scenarios are reduced to 10 by 990 iterations. So this is the method of, this is the algorithm of SCUC. So we have basic data input, thermal, wind and CAES unit. We have the uncertainty characterization of wind power, scenario generation of the wind powers, and then reducing, like 1,000 have been generated and reduced to 10. And then we do the generation, operation, and optimal use, unit commitment, mixed integer programming. We check whether it is feasible. If no, it is infeasible problem. If yes, we go here. We do early network security evaluation. If there is a violation of security, yes, we go and do the we use the feasibility Bender's cuts because this is a Bender decomposition problem, and we cannot cover this in 1 hour. So the major thing is after violation we go to generation dispatch and optimal UC again, and we again run this program by using certain changes, and then we get the feasible solution. And once we get there is no violation of the security here, we go to parallel network security check with wind scenarios. If there are violations, we go to again. If not, we end. So we have run this data on IEEE 30 bus system, and we've got these results for the IEEE 30 bus system. So what our discussion is that how SCUC is important. So let us discuss. We are more into these equations and how SCUC is important for system operation. And as and on you increase the number of components in the system, the complexity of the SCUC increases. And as the problems become more nonlinear, subjected to large number of constraints, you need a better optimization software to run this program. The largely used optimization software is GAMS, which is being used by Grid Controller of India as well. They are going for SCUC, and they have developed, as far as my knowledge goes, a program of SCUC in GAMS. So GAMS is efficient to handle large number of variables, because as the system size increases, the large number of generators which are into large number of wind generators, thermal generators, transmission line constraints, transmission lines, since all these are variables, so the large number of variables are known to be handled by GAMS easily. So, but there always a trade-off between the complexity and the accuracy. If you increase the complexity, the accuracy increases, but yeah, of course, computational time is huge, and sometimes the problem becomes infeasible. The software does not support the solution of such highly complex problems. So SCUC is a very challenging problem, and uh, running of the SCUC on simple uh, optimization platforms is difficult, because it contains large number of equations with, so it contains the equations of the generators, the transmission lines, and these network security constraints. All these lead, and whether, since this what equation I've showed is DC-OPF, if you go for AC-OPF it is more difficult. So if you read the literature of SCUC, you will come across that ACOPF is not that successful on different software platforms in comparison to DCOPF. So DCOPF is highly used in place of ACOPF. DCOPF means that we are considering only line to limit criteria. ACOPF has voltage and frequency criteria as well. So this is from my side. Now I request, if you have any questions, you can ask. Are there any questions? Because I'm unable to see. There is one question. Instead of Monte Carlo based probabilistic scenario generation, if we use data driven AI model, based scenario generation, will it be more realistic? It is also one of the methods. We have not worked on data-driven AI model-based scenario generation. We have worked on Monte Carlo simulation, and we have the amount of literature, since we have been working on uncertainty modeling in many of the applications like SCUC also, and like one of the thesis which we did was um, electrical vehicle integration. So we worked on electrical vehicle aggregator. So we use Monte Carlo simulations there also, and whatever literature we have read, Monte Carlo is highly used. So and it's very simple. But Monte Carlo, the main disadvantage of Monte Carlo is that it is scenario based. So you generate large number of scenarios, and if you use all the scenarios, your problem is more computationally, it requires more high computational effort. Uh, it takes a lot of time. So another thing is, unless and until you generate large number of scenarios, you are not able to completely, uh, uh, model that uncertainty. So, and it leads into high computational efforts. So you need to do scenario reduction. So when you do scenario reduction, like in this problem, what we did is 1,000 scenarios and then we reduced to 10. Your scenario reduction algorithm should be very efficient so that the complete pattern is depicted in those 10 scenarios. Since SUC itself is a very complex problem, and if you use large number of scenarios, it becomes time consuming, complex. So less number of scenarios were beneficial. We had our problem settling and we were able to, analyze the results. But then scenario reduction algorithm should be very efficient. So this is what we know about Monte Carlo. Data driven AI model means um, we do not have any, say on this because we have not worked on it. You can try, but Monte Carlo is many times discouraged because of large computational effort requirement. It also depends on the research, like when whatever is prevalent in uncertainty handling or uncertainty modeling, that should be used. If you find in any paper where AI based scenario generation or data driven models are there for uncertainty handling, you should definitely go for that. But you should look into how complexity is reduced. Any other question, please? Over to ICT Academy. This is what we have completed the lecture, and if any other inputs are there from them, we can go ahead, or otherwise we can wind up the lecture.
Thank you so much, ma'am. I
Thank
think there are no questions from the users, so we can wind up the session.
Okay, thank you all of you. It was very nice, and thank you for your patient hearing. Thank you very much.